Dean Peter Trappa of the College of Science and Dean Darrell Butt of the College of Mines and Earth Sciences. We really thank you for coming this evening. And both of them, unfortunately, are not able to be here tonight because of a Martin Luther King Week event that has a lot of the administration involved. So you're stuck with me. So my name is John Horrell. I'm chair of the Department of Atmospheric Sciences. And it was a real distinct pleasure to be able to invite one of our alumni, as well as a colleague for many of us, to be here tonight and talk about his research. So Craig Clements is a professor at San Jose State in the Department of Atmospheric Science. Well, they haven't changed yet, Department of Meteorology, but they have a good title in there, Climate Science as well. It's one we've been thinking about. Craig received his Bachelor of Science from University of Nevada, Reno, and then joined our program as a graduate student in the late 1990s and started working with me. And it was, I describe it as there's some graduate students, and I think most faculty can recognize this, there's some graduate students that you're kind of helping along and steering them and guiding them and making suggestions and hope that it takes. And then there are some graduate students that come in and have a really clear idea of what they want to do, and they tell the faculty what they want to do, and sometimes we actually do it, and Craig is one of those, because he came here with a very strong interest in being involved in field work. And that was not my cup of tea. So I had to go out and find funding and some equipment so that we could start a field project in one of the most ungodly places in Utah, which is Peter Sinks, the coldest place in Utah. Fortunately, we were there in September rather than January, and it was cold enough. After that, Craig went to the University of Houston, and that's really where this story starts, because that's where he got involved in wildfire research, and that's really why he's here tonight and everything else. So I accept no credit nor blame for everything that Craig has done since. It's really pretty fantastic. And I do have to say, though, it was Craig's drive that really started a lot of our work here in experimental field work. And it really was sort of a way that our mountain meteorology program took off. One of Craig's mentors became one of our distinguished emeritus faculty, Dave Whiteman, who's around here somewhere, and there he is hiding way in the back. And so that has been sort of a major part of our program ever since. Since that time, Craig has joined the faculty at San Jose State in 2007 and has progressed through there. He has been doing this groundbreaking field research on wildfires since. He created the Wildfire Research Lab, and now the San Jose, just because of the major impact of wildfires on the state, is growing in terms of just the number of faculty positions in the area of wildfire and the impacts and economics of wildfire, and that's really due to Craig's effort. Craig has been supported by the National Science Foundation, received an early career award, has been supported by many of the federal and state agencies in terms of his research. He's published dozens of papers in the area of wildfire atmosphere interactions. He's, a frequent person that is asked to come and explain the unexplainable, as you're going to see. Just, what is the science behind what goes on in wildfires. So that includes testifying in places that I wouldn't want to have to testify, and then also getting that training to really be able to deal with the media and explain this, whether it's New York Times, CNN, and even the more prestigious places like Rolling Stone. So that's, he was, and we may see some clips from this, I think, part of a fantastic documentary by the NOVA PBS program as well. So with all of that, I just would like you to help welcome Craig here for his presentation.
Great. Thanks, John. Good evening, everyone. I want to thank you all for coming tonight, and I want to thank you all for the invitation. It's a real honor to be in this lecture series. I admit I was asked, Steve said, hey, you want to come out and give a seminar at the College of Science? I said, yeah, sure. And I didn't realize it was my first day of classes today that I had to cancel to make sure I got here. And I didn't know what the legacy of this lecture series, so it's a real honor and pleasure to be here. Let me get my presentation up and loaded. Okay, so I want to talk to you today about some of the advancements in monitoring the wildfire environment, and particularly from an atmospheric perspective. You know, I'm trained as a meteorologist here at the University of Utah, and so that's kind of how I've taken a look at the wildfire problem, is from a meteorologist's perspective. So I'm going to give you a little background on wildfire science and kind of just give you an idea of, before I get into the details of what we do and when we look at wildfires, is kind of what is the fire environment? And if we look at a picture, this is a prescribed fire east of San Jose, but this is what we call the fire behavior triangle. And so we have topography, we have the fuels, the stuff that's burning, so I'll refer to fuels all the time, and then it's the weather. And the weather is the most variable. And that's really, when you think about these big impact fires, the Camp Fire, the Tubbs Fire, the fires in Australia that are ongoing right now, these are weather impacted events, large weather events. And you think in California, oh, our students in meteorology are like, oh, we want to go to Oklahoma, or we want to go to the Midwest, we want to see weather. And I was like, we do have weather, it's just sunny weather. Okay, so what starts most wildfires? I'm sure most people know this, but only you can prevent wildfires. But it turns out it's humans. 88% of wildfires ignitions are caused by humans. It's not necessarily arson. Most of the time it's accidental. And natural causes are only 12%, and that's usually lightning, right? So at times you can have like one time in 2008 in California, 3,000 ignitions in an afternoon through a lightning event. So that's a lot of ignitions. That's more than you would expect. But it's the big events that are really troublesome. And if we think about wildfire around the world, it's common. I mean, wildfire exists basically everywhere except fuel-limited areas. Hyper-arid deserts, alpine environments. And as the climate warms, that may change. It's changing. Wildfires are getting to other areas, the cryosphere, obviously. And so we can expect wildfire across the planet. But we should actually maybe not expect these extreme wildfires, or maybe we should. I'm not going to go in there tonight into that topic. I'm going to be really talking about kind of the dynamics of wildfire and fire spread. And so the red flag warning, many of you probably have seen that or heard about the red flag warning. It's basically well, I haven't gotten there yet, but like when we think about red flag warnings of fire weather, we're thinking about hot, dry, windy conditions. This is California weather. This is why the rent's so high in San Jose. I tell my students, I go, well, the reason why it's so expensive in California is because it's always clear and perfect weather. I mean, it really isn't. And so we have the red flag warning. This is basically relative humidity and wind speed. And this is what drives a lot of wildfire spread. And so if it's dry and it's windy, you can expect fire. So if you look at the Camp Fire, very windy day. That was in November. It was very, very dry because there was no precipitation. I'll talk a little bit about the Camp Fire later. And so these are the conditions that we are trying to better understand. But what about fire danger? So we have fire weather. Those are the conditions. It doesn't mean that it's always going to be high fire danger. So fire danger takes into account not only the weather, but also the fuels and the fuel condition. And so when you see this sign, if you go to a state park or a national park and you see this sign, that's manual. Somebody has to put that sign up, unless it's, I haven't seen a digital fire danger sign yet in the western US. But so what's very high? How do we determine that? So that is from the National Fire Danger Rating System. It's a very elaborate system of calculations that take into account that fire behavior triangle of topography, weather data, and fuels, both dead fuels, so cured fuels, and living fuels. So we call those live fuels. And I'll talk about that next. And so the output of what we call NFDRS, or National Fire Danger Rating, allows us to provide day-to-day fire operation calculations for fire managers. Where do we need to put resources? In California, we might, for a Santa Ana wind event in Southern California, all the resources in Northern California will move to Southern California over the course of a day. And anytime during that event, you'll be driving the freeway, you'll just see fire trucks just rolling down the highway because they're moving the resources based on the fire danger rating for that week, let's say. Thinking about live fuel moisture, so these are my students, my graduate students, that are sampling chamise fuels. These are shrubs. This is a very common shrub throughout the western US, in California, coastal California. And we can see that the fuel moisture goes really, really high and really, really low in the fall. And it's basically the ratio of water content versus plant material. And basically, you have to manually sample that, clip it, put it in a can, dry it, weigh it, dry it, and then re-dry it, weigh it, the next day. And so it's a manual labor. And it's a key component of the National Fire Danger Rating System, but we don't have a good handle on live fuel moisture, and we don't understand how the weather really impacts it, so it's still a big consideration. So moving on to fire behavior and fire behavior modeling, when we think about fire behavior, we think about how fast does the fire spread? Is it going to get to this community at this time? And so we call that rate of spread. And there's, as you can see, so Sullivan et al., or Andrew Sullivan in 2009 presented this figure where he looked at a bunch of different models. Most of them are field-based, some are lab-based, and you got some linear relationships, different relationships. And so there's no one fits-all solution in terms of fire spread and wind speed relationship. And that is because you need to couple fire spread and the heat of the fire to the weather. And so that's where this fire-atmosphere coupling and the fire-atmosphere interaction comes in. And that's where our research comes in. We're trying to understand those two components. And that led us to this. If you think about the Carr Fire tornado, anybody remember this? It was a EF3 tornado 2 years ago outside of Redding. I was able to go to the site with the Forest Service and take some pictures. This picture went viral. I got in trouble from CAL FIRE for posting it on Twitter. It's a gas line wrapped around a tree. And so, yeah, nobody had really seen this in terms of fire behavior before. So this is a very extreme event. With all that, with all like the fire danger and fire weather, we still don't have a good handle on how wildfires create their own weather. And that's where my research comes in. And I'm an observationalist. And so I like to go out and collect the observations to better understand this problem. And so if we need to get the observations to better get a handle of this kind of idea. So if a fire is if it's really, really windy, this is called the convective Froude number. It was proposed by Byram in 1954. And it's basically just the ratio of the wind speed versus the heat of the fire, okay? And so we call this like plume dominated. If it's not so windy, but it's really, really hot, the plume should stand up, and then all the circulations around the fire should be associated with just the fire itself. If it's a really windy event, the plume's tilted over and the fire is being pushed by the wind. And so, you know, we could argue back and forth in the literature about if this is really appropriate, but it gives us an idea of what we're trying to measure in the field. And so with that, it turns out if we think about meteorology or atmospheric science, there's not a lot of meteorological observations near active wildfires. There's a handful of weather stations, which are great. But those weather stations are designed to kind of calculate fire danger. They're not really trying to look at like what the fire is doing at any one time. And so we have a limited understanding of how plume dynamics and the plume in the column affects the fire spread. And there's also a data gap for testing these next generation fire behavior models. And so my goal is to better understand this interaction between the atmosphere and the fire and to collect comprehensive data sets from both experimental fires, which I'm going to talk about next, and large wildfires, so deploying to active wildfires to collect those observations. And so this is a field experiment that was conducted in 2013, and so this is actually under red flag warning. It was very hard to get this done. There was a little bit of politics at the last minute. The county judge shut us down and said, we're not putting fire on the ground, statewide fire ban. And I was like, what? We got all these scientists from the Forest Service all around, and we want to put fire on the ground. It's, you know, it's private land. It's the University of Houston. It's just a grass field. And so this is a picture of that tower that is actually showing the fire front moving in. And then the composite here is, let me explain this picture here. what you're seeing are these black dots in an array, a grid of pressure sensors and temperature sensors. And so as the fire front moves through that field, temperature goes up, we know where the fire front is. We also have these wind vectors, which are anemometers, which are wind sensors placed around the burn unit. And so what you're seeing is as the fire, okay, let's start out. As the fire approaches these sensors, there's the fire, the big dot. The shading is also wind speed from a Doppler LiDAR. So we see the strongest winds are occurring at the fire front. And so that's pretty exciting. And if we take the data off the tower and we plot it, this is temperature. You can't see those numbers, but it goes up to 350 C, and that's like right here. These wind vectors are basically compass bearing, so these are northwesterly winds that accelerate. And this is the plume outline, so this is the hot temperature of the plume. And so what you see is the fire front, this is ignition, and this is the fire front passing the tower right here. And all the temperature sensors are up this tower, and all the wind sensors are located at these different heights. And what we see is that the pressure drops right at the fire front. And that low pressure is accelerating the wind through the fire. And so it's causing an advection of the combustion gases from the combustion zone to move forward towards the fuels. And so this has been shown in some laboratory experiments as well. And so the advection of these combustion gases ahead of the fire front causes the ignition of the fuels. But we can't really see what's happening at the fuel line here. So there's another set of experiments that we've worked on from New Zealand. And these were conducted 2 years ago. And we had a number of instruments out here. And these experiments were set up to test this theory of this flame peaks and troughs, where this is from the Missoula Fire Lab. Mark Finney's team came up with this theory that, you know, it's mostly convection, it's not radiation. I mean, we know it's some convection. We call it advection in atmospheric science. We've got horizontal convection, so hot gases moving across the surface. But they saw this in the laboratory and saw that the winds are moving through the fire front and pushing it down. And that's where you get these flame peaks and you get these troughs. And if we look at it from a video, so there's some video cameras out here. Uh-oh, come on. That's interesting. I was told bring lots of videos. Let's see. This is going to be, hold on. It was working for like all day long as I was practicing. Let's see here. There we go. Let's see. I always had this problem. Brand new laptop too. State of the science. Oh my goodness, what's going on? Yeah, I'm picking, there. What arrow?
You might not see it on your screen.
What arrow?
There's like a play right there.
No, I was clicking that. No.
Is it? No, it's not. See, look where it goes. See?
Oh, yeah.
So,
look
yeah,
at that. I'm using that one. Thank you. I wasn't too crazy. Okay, so we got to play that again. So you can see how there's lots of turbulence going in through here. Right? Did you all see that? Should we, well, we're going to do this again here? Let's go like that. There we go. Okay, here we go. And so you can see the flames are really close to the surface, right? If we look at the infrared image, at the same time, there we go. There we go. You can see the hot parcels being advected along the surface. So the hottest temperatures are the reds, okay? They're being advected out front. And then the lighter shading here, this is, you know, a lot of entrainment, so the gases are cooling, but the hottest temperatures, so that's advecting across the front. So with these smaller scale experiments, we can see that this is the process of fire spread. Okay, so that's flat terrain. This is stubble. Fuels. Fuels are very complicated, so if you want to like do an experiment, you want simple fuels. So what they do is they go and they cut the grass down so it's perfectly uniform. It's like a lab. So we're like using the outdoor farmland as, you know, these fields as a laboratory. But let's think about tilting the terrain. What about fire behavior in canyons? You know, we looked at this fire spread through the flat terrain, which we use a lot for validating our numerical models of fire spread. But it turns out canyons are very dangerous. And we call this eruptive fire behavior. Dominguez-Villegas proposed this term because it was similar to volcanic eruptions as the wildfire accelerates. It turns out that wildfires accelerate exponentially in canyons, but not really on flat ground. And so we also call this blow-up fire behavior. Okay? So you hear a blow-up fire or eruptive fire behavior. And fire eruption is not rare. It happens a lot. And where a lot of wildfires occur, we have lots of mountains. California, Intermountain West, the Rockies, et cetera. And so if you think about firefighter fatalities, more firefighters are killed in canyon terrain than on flat terrain. And so these are just some major fires. Man Gulch is very famous. You've got, let's see here, the Palasca in Corsica. I went and visited that site. It's a nice narrow canyon coming up from the beach. 3 firefighters were killed as it overran them because you see the fire in the ground and all of a sudden it's like, it's probably good. It's a kilometer away. We're fine. And then pretty soon it overtakes and they get burned over. And so lots of firefighter fatalities. And so Dominguez-Villegas and his lab have developed these laboratory experiments where they can see acceleration in the lab, where they put an ignition in these fuel beds and they can tilt the laboratory bed in different directions, and they can see that the thing just rips up the canyon. This is the base of the V-shaped canyon, and then it accelerates up the sidewalls, and so you get a lot of explosive fire growth. And so with that, you can see this relationship where this is area burn from laboratory and using an analytical model they came up with. You can see it's this exponential growth in a short period of time. So it's fairly constant, all of a sudden it grows, and that's that propagation up the sidewalls. And so how that happens, well, we think, is that if you have a tilted slope and you have a fire on it, you have limited entrainment on the upwind side because you have the terrain, right? And so you can't get air on the other side to tilt the flames up. So if you had a campfire, everybody's been around a campfire, and you can see the campfire is pretty circular. And so if you put a wind on that campfire, it tilts over. In a canyon, the fire naturally tilts over. One theory is because you get more fire-induced flow from the backside because you can't get it on the upwind side. And so that enhanced convection and radiation to the fuels. And so that's how fire is explosive in canyons. And we can do that in the laboratory, but we've never done it really in the field. My field experiments, I'm not going to come here and tell you about my failed experiments. That wouldn't be fun. We tried to do this on some slopes, and it didn't go as planned. So we're going to try to go to the Pyrenees next year and burn a 1 kilometer long canyon from the bottom with a head fire, what we call a heading fire, up to the top. And so the problem is, this is the French border here. And so we have to burn it. We have to burn it in winter because they want snow on this side in case it spots over into France and causes a wildfire in the forest there. So a lot of moving parts. So we're just starting to plan this experiment, and anyway, so that's pretty exciting. So that's kind of the next phase in some of these smaller scale field experiments. And we've learned a lot from doing these small scale field experiments. But what about sampling large wildfires? This is where I think it gets really interesting, because these are bigger fires. They're obviously more intense and hotter, and you're not really in control. You're not putting the ignition on the ground. And so this comes up to our RaDFIRE program, which is basically pretty ongoing. And so the idea is rapid deployments to wildfires experiment. And this is part of my NSF Career Award. And so came with the idea, let's just go out and sample this stuff with the same tools we use for our experiments. And so we loaded up a truck, and this is the Paradise Fire on the second day. After forcing my students to sleep in a Denny's parking lot in Orville, California after the first night, I'm like, it'll be fine. And it turns out that is exactly where you do not want to be at night. And so we went out here, and yeah, that's a long story. And so the idea is that we really want to have this plan for rapid response deployments to study wildfire. And so this allows us to have obtained new observations in the fire environment. There are very few coordinated field experiments on wildfires. And so because it's logistically hard. I mean, it's maybe not as hard as like hurricanes or tornadoes, but there's a fire agency managing the land for many, many miles around it, and to get in there with your tools is not easy. So it turns out that everyone has to be fire line qualified, and we want to make observations from the fire front, from the active fire front. So all my team members, all my grad students become firefighters and are red carded through the US Forest Service. Everyone's listed as a national resource, so we can be ordered to an incident. And we provide data to the incident meteorologist, the fire behavior analyst, the FBAN, and incident command team. And sometimes we get requested to come in and like do profiling for smoke, for the aircraft operations for suppression. And so let's see if I can do this one. There we go. Oh, I didn't know there's volume. Hopefully I don't say anything. So this is during the Kincaid fire with 50-mile-an-hour gusts. The fire is approaching my team. These are students. And of course, I told them, make sure you clear around the new radar truck. That is priority. And so everybody's wearing their fire shelters. We didn't bring enough shovels, obviously. And so we were actually integrated with the incident. The FBAN called us at 3 a.m. and said, "Are you all right?" Like, we're fine, we're actually leaving out of here. And it turned out the most dangerous aspect of that fire deployment, and we'll go into a little more detail about that, were the fallen trees, the branches on the road. And this is the first time we deployed the radar, which I'll talk about in just a bit. So we've been out to a couple fires using LiDAR, and this is a laser-based instrument that we can, oh, here I am again using that. So we can get really high-resolution, detailed observations of plume structures by using our LiDAR and scanning the plume. And so this has allowed us to sample over 30 fires. And that was our first program overview paper where we just used LiDAR and some aircraft-based radar, which I'll talk about. This is the campfire deployment. And we didn't really know what we were getting into. We heard there was an ignition in Pulga, didn't know where Pulga was. And so I called my students and said, hey, let's go, there's a fire. And it turned out NOVA was out there, and they kind of helped us understand where things were. And this is my grad student, Matthew Brewer. We're operating the LiDAR here, and we're in active fire suppression right on Pence Road, which was we call this the southern flank here, okay? And so what you're seeing here is the backscatter from the LiDAR. So it's a laser beam shooting up, and it's getting all the smoke particles. So that's the depth of the plume, about 1 to 1.2 kilometers. And these are the vertical wind profiles that we sampled during that time. And you can see it's north-northeast winds. We compared the mean LiDAR profile from our numerical simulations of WRF of this case, which was just published this couple weeks ago. And we can see that the LiDAR actually, that's the ground truth. Those are observations. But the numerical weather model, the prediction, is much greater. And so it's trying to do this downslope, low-level jet here, this kind of nose structure here. And here it gets the structure a little bit better. We're only plotting up to 900 meters, even though we had a few more samples up here. And so it's important for us to get these observations because we want to be able to model these catastrophic events so we better understand what was causing it. So this is a wind-driven fire. The smoke remains in the lowest kilometer, and the fire spread was associated with long-range spotting. And you probably heard about the campfire, and if you've seen pictures, it's like the forests around Paradise weren't burned. The trees were not burned. But the spots, the embers, which I'll show you next, they were landing on homes. And those homes had pine needles on them. They had pine needles around their structure. And so those houses caught on fire, and then they burned the next house, they burned the next house. So if you look at those photos, it's like, wow, the forests are still all perfect. It's because the embers went through the forest, the trees, the ponderosa pines can handle the embers, but the houses cannot. So that's more of a social problem that we have to figure out our resilience in our building. But this is what it was like when we decided to finally leave our location. This is a GoPro, this is the LiDAR, this is the truck. And I'll show you some of this fire spread here. So the fire front's approaching here. Those are probably 80-foot flame heights. And now you'll see the ember wash. So this is how fires cross the road. This isn't a very particularly windy event, but it's getting dark. I've got undergraduate students with me, and it's a campfire, and so we wanted to get out of there before power lines might come down. So there's a sense of safety that outweighs the data collection need. So what about measuring big plumes? We had the opportunity with NSF to fly the Wyoming King Air on some fires. And so this is the Pioneer Fire in Idaho in 2016. And this was an exploratory flight just to see how the cloud radar would perform. And so here's the Wyoming King Air. It's got a cloud radar pointing down and up. And so it's got 50-meter range gates. And so Dave Kingsmill, I think, took this picture. And this is at like 15,000 feet above sea level. The plume went to 27,000. They could barely get above it, and they flew through it 3 times. They measured an updraft of 39 meters per second, and the radar, the scientist didn't wear a seatbelt because, you know, I don't know, I didn't fly on this plane, and so they were pretty much like, yeah, it's fine. I forgot. He cracked his head open and bled, and we were chatting with my students, like, what's going on? You know, this is really interesting. But the data are amazing. This is the radar from the flight level, this dashed line, and I have a graduate student that's finishing up this analysis, and this point here is the maximum velocity, which was 58 meters per second, so about 130 miles an hour vertical updraft. It's very far off the ground, so there's lots of dynamics that we're trying to investigate why that occurred. There's also I could be lying here too, because this slice may not be perfectly in line with where the updraft core is. We might be we're just getting it downwind, so it actually might be stronger. But anyhow, we know now that this radar works really well. And when they sampled through the cloud, we see lots of small cloud droplets and non-zero, what we call pyrometeor concentrations. We don't know what these are. They're ash, and they're things, leaves and stuff, and I'll show you some examples of that. And so that's what the radar is actually seeing, is the ash. And so flying through Pyro Seabees is problematic. It happened, I don't know if you saw this. I'm sorry, it's a little blurry, but this is a little clip from Twitter, but passengers described flying through the fire-generated cloud in Australia. All of a sudden, it just pitch black, and that's when the plane sort of dropped. People were vomiting, people were swearing, and you know, it was pretty gnarly. And it turns out when the pilots, you know, there's a avoidance radar, I think it's X-band, in the front, they didn't see anything because it's small particles, and the X-band can't see it. Same thing on the King Air. They didn't see anything, like, yeah, there's no problem. So the pilot was like, let's go. And they get in there, and it's like, oh, no, what did we do that for? And then they did it 2 more times, and then they said no. So there are some implications to understanding what's going on. But with that, we also have to think about what radar reflectivity is. I'm going to talk more about radar. I'm going to show you our new radar. But this is what this is a leaf that's smoldering. And Nick McCarthy just finished his PhD. He was visiting me. He's an Australian student working on radar and wildfire plumes. And he spent a summer with me in California. And he came up with this wonderful diagram of kind of looking at the different processes that affect pyrometeors. So you actually get some soil entrained into the plume. The paper, it said, I think it's like almost 40% of some of the aerosol, 30 to 40%, which is really high. I don't know if I really buy that, but whatever. And so smoldering ash, and there's ash density, varying with turbulent flow. There's all these different things. Here are some raindrops that he collected with some ash particles. This fell out during the Kincaid fire about 50 meters from our radar. So now we know what we're seeing, but we still don't know what the radar is seeing in these. And so this is Nick's radar, which is some of the first X-band, mobile X-band radar deployments on wildfires. He's got it on a trailer. This is his PhD program. Here's the fire plume. Here's a pyrocumulonimbus that's developing, and he's scanning it. And some really interesting data. And I just want to explain a little bit about the dual pole aspects of radar. And I'll just give you this slide here next. So the dual pole radar actually has horizontal beams and vertical beams. And when they intersect particles, they can determine a little bit about that particle, whether it's round or flat. And so we have what we call DBZ, which is horizontal reflectivity. And here you can see the strongest is downwind of this. This is a rain column. There's a thunderstorm downwind. Here's the smoke plume. ZDR is differential reflectivity, and that's the difference between the horizontal and vertical reflectivity factors, and that gives us kind of an idea of shape of the particles. And then correlation coefficient is basically a measure of how similar the horizontally and vertically polarized pulses are behaving within that radar volume. So, for precipitation, we use this a lot. Radar scientists use this a lot. This is the first time we really started looking at this for wildfire plumes, because we don't know really what's in a plume because it's really hard to sample. And so you can see here in the correlation coefficient, you're getting values close to 1, so that's more like rain. This is the rain shaft here. But in the plume, we're getting values of 0.2 to 0.4-ish. And so this gives us kind of insight on what we should expect. And so from Nick's results, from our aircraft results, we went back to NSF and proposed to get a mobile radar. So this is the mobile radar at the Kincaid Fire, and this is in Utah. And so I'm not going to go into a lot of details of this just for the sake of time. Highly mobile radar, very high resolution. So we get up to 7.5 meter resolution out to 15 kilometers, depending on what we're looking at. It doesn't always work that well. Its wavelength is 8.4 millimeters, so it's millimeter wave, Ka band, designed for clouds and droplets. So we thought this would be a nice radar for ash. And so this is our first deployment. This was, it arrived in August. We got the leveling jacks mounted. Students did all the work. We got the truck all sorted, and there was a fire in Yosemite. So it was perfect. And we found this view on Google Maps. And I actually had a visiting colleague from France who wanted to paraglide in Yosemite. And so he's like, well, can I bring my paraglider? There's a site here. And I was like, yeah, but you're probably not going to be able to paraglide during a wildfire. But he was able to find the site for us. So he's like, oh, this is it. This is perfect. And I said, no, there's a TFR, a flight restriction. There's air tankers and stuff. But he thought this was pretty cool. So here we are scanning this plume. It's actually 13 kilometers away, so it's very coarse. So don't think that this is the only data that we can collect. But what you see, if you follow this, you can see what we're calling these pyrometeor reflectivity cores that are punching vertically all the way to the top. And they kind of fall out the back side. So there's enough energy that this biggest debris and ash is going all the way through. And so that's pretty exciting. So the Kincaid fire, a few days later, or a week and a half later, breaks out. And I was grading, and it was 10:30, and I get a text from Nick, who's still visiting California, and said, hey, there's a fire. You want to go? I text my students. They were actually in bed at 10:30. Which is weird that the professor is like, hey, let's go, get your stuff. Who can drive? I had wine at dinner. You're driving. No, just kidding. So we left the university at 11:30 p.m. and we got to the Kincaid fire that night. It turns out the next day there was this is the first night it ignited, there was not a big wind event, so I'll get back to this PSPS, but PG&E 4 days later had one of their largest public safety power shutoffs, which is a big political issue in California. Everybody heard that PG&E and the energy companies are turning off everybody's power just for fun? If it gets windy, if it's hot, dry, and windy, they definitely turn it off. And so trying to figure out when they turn it off is a big issue. So this was the second night of our deployment was a PSPS. That's when I showed you the movie of the students scraping the ground because it was blowing 100 miles an hour on the ridge tops. But our first night, oops, sorry, I'll just give you a map. So our first night, here's the fire perimeter. Our first night we were right here about 1 to 2 kilometers from the fire. It was just burning over here. And we were in this very nice vineyard that has great Cabernet in Alexander Valley. And it turns out the vineyards are really, there's no fuels. It's very safe. But the fire is approaching us and dropping ash on us. So that was great because this is what we're actually seeing in the radar. And so here's our deployment. And it was a wind-driven fire. So this is reflectivity. So this is the energy back from the radar, from the particles. This is velocity, Doppler velocity. So greens are toward, the reds are away and greens are towards, and you can see the flow is moving this way. But look at this, there's red down here, so we're getting like an eddy, a lee side eddy, little vortex is forming. And you can see the plume is punching up. So these are much higher resolution images that we were able to capture. Large ash and firebrands, the smoldering or glowing leaf that fell down, and sticks and stuff were falling out of the plume on us. So of course it looks perfect. Right? The second night, that windy night that we went, we took both the LiDAR truck and the radar truck. So we're able to do vertical wind profiles with the Doppler LiDAR and scan with the radar across the fire. And so here's the fire kind of moving this way, and this is the next morning. And the problem with these deployments is that we're leaving at 7 p.m. We're going to check in with the fire operations or the incident command team, and we want to get deployed by 10 p.m. before these winds hit. And we were able to set up like 30 minutes before the winds came to the surface. So it's a great case. And this is the case where the power was shut off in Northern California. And we saw it as we were driving across the bay, and all of a sudden, the North Bay goes out of power. It was really surreal. But here's the plume. And this is a horizontal. This is called a plan position indicator, a PPI scan. So we're taking the radar and we're scanning above the terrain, and we're just doing this, okay, back and forth. And because this radar is brand new, it's very fast scanning. We can scan 20 degrees per second, which is much faster than our LiDAR. And so we're getting multiple scans. We're able to do volumetric scans of this plume. And so you can really see where the highest reflectivity cores are. And I'm not showing what they're associated with the most turbulence, which we call spectrum width. And so this is where the plume is punching up, and then it's being convected downstream. So it's a really nice data set. So we're analyzing these, and these are fairly new data. And it's the first time we've actually deployed this radar. But what I want to show you is what's called the FASME. This is the Fire and Smoke Modeling Evaluation Experiment. And there is a prescribed burn just south of here, about 2 hours, in the Fish Lake National Forest that we had an opportunity to sample. It's part of a kind of a interdisciplinary fire research program. And so they did an ignition on the 7th of November. It's a prescribed burn for aspen ecosystem restoration. And so what that means is that they're trying to burn the conifer, the mixed conifer, and they're trying to kill them. So they're burning high-intensity crown fires. The crown fire is when it burns into the crown of the plant and rips. So we set up a couple of LiDARs. Neil LaRoe, who also did his PhD with John, is now at University of Nevada, Reno, and he brought his LiDAR, and we set up our LiDAR and our radar, and we were about 3 kilometers from the burn. And these are what the data look like. So this is a prescribed fire, by the way, that went to 7 kilometers above sea level. It was seen I think in Colorado, Salt Lake, and in South Utah. And so here's the radar, and here's our LiDAR, and then Neil's LiDAR is way over here. But here's the reflectivity, here's the velocity, and this is just the initial ignition. You can see the highest reflectivity, these pinks, stay at lower altitudes. So these bigger debris are falling out probably and not being pushed up high. If we looked at differential reflectivity, we're not seeing too much structure until a little bit later. And if we look at the correlation coefficient, we were hoping that because it's a cloud radar, that the correlation coefficient would indicate where the cloud top base is and where the cloud is, and where the kind of the ash core is located. And what we hypothesize is that these cloud droplets are so small that the radar is actually can't measure those very well, as we were told it wouldn't. But we're seeing all the ash inside those clouds. So inside the pyrocumulus cloud that you see on top of wildfires is filled with ash and debris at that altitude. And that's what these radar observations kind of indicate. And so here's another set of scans. I mean, look at these structures. This is at 15-meter resolution, scanning 10 to 12 degrees per second. And we were there for hours. So we have a lot of data. And here's the correlation coefficient. I don't have time to show you, I don't have the fixed images, but you do see a little bit of difference. We're getting slightly higher correlation coefficients aloft, but it's really noisy, so we still have to apply some filtering. But look at these velocity structures. Okay, the radar's here, and it's scanning vertically, so it's doing a slice through just real strong vertical cores of pyrometeors being punched up vertically. And so that's what it looked like, I think, from Cedar City or somewhere. So this was a big event, and it was on satellite. I didn't point that out earlier. So what's happening at the surface? What about the fire behavior that's causing the structure? This is a prescribed fire. They lit it with a helicopter. So there's a helicopter going back and forth, dropping fire on the ground to get these things to burn. And I don't have a lot of photos of the crown fire, but I do have the infrared image. So what is, oh, I got to do this again. There we go. So this scale should be doubled because it has to be recalibrated. And so these are crown fire from this angle So we're able to use, this is a new camera, it's the first time we put on a crown fire. It hasn't saturated, so we're seeing some lower intensity, but you'll see these real nice flame structures propagating vertically, detaching, just like in the field scale experiments where we see these flame structures moving horizontally. Here, they're moving vertically, right? Because there's no wind on this day. This was a plume-dominated fire. The plume went so high. So we're getting nice structures with the thermal imagery. So we want to go back and do RaDFIRE 2. And we have a pending proposal soon where we're going to take 2 DAO, the Wyoming King Air, which we're going to instrument with a 3-wavelength infrared camera system. So we will have, for the first time ever, coincident fire behavior measurements, high resolution, with vertical velocities. And so we'll really be able to understand what the fire is doing and what the flow structure associated with that fire front, while scanning it in a volume with 3 radars, 2 dual pole, and 2 LiDARs. So it's going to be the most unprecedented data set to date. And so that is our goal. So I'm not going to do a big summary here, but my key points are close range observations can be made at active wildfires. The teams have to be fire line qualified. You can't just show up if you need to be on the fire. It's very difficult. We've demonstrated over the last few years that mobile remote sensing observation systems are ideal. I prefer agile platforms, and with fast leveling systems. I didn't mention that our radar truck, we're using off-the-shelf leveling system that was actually not very expensive, and we can level that truck to within 1/10 of a degree in 3 minutes. And so if the fire approaches, you can pull those jacks up, hopefully, and get out of there as well. So it was really important that we have that agility to go to these things. So with that, I'll thank you and take any questions.
You've been able to learn stuff from Australia's experience that can help us here?
Yeah, they had so the question was, are we able to learn from the Australian experience to help us here? That's a unique case. I mean, they have 160 ongoing fires in remote areas, so it is the fire weather that helps drive that. They came out of a drought, and so the fuels are critically dry, and they're in their summer season. But they had a case, and I don't remember the exact date, where they had, 20 pyrocumulonimbus, so 20 Pyro Seabees events all at the same time, many of them lasting 36 hours or more. So that we've never seen. And so that's that's exciting. That's extreme. Okay, so that would be a nice case study. So I would imagine there's going to be lots of research coming out of those cases from both the Australians and a lot of Pyro Seabees scientists here in the US. Yeah?
Can fire burn underground?
Yeah, so the question was, does fire burn underground? Yeah, we call that actually ground fire, whereas fire burning above the soil surface, we call that surface fire. And so a lot of times, fire can burn into trees and get into the root system and continuously burn. And then there's the peat fires that can actually continuously burn in the soil and below ground and remain smoldering for months. And so yeah, fires do burn underground. It's not as catastrophic of an event versus a surface fire or a canopy fire, crown fire. Yeah?
Can you give an example of how some of this research is informing advancement?
Well, right now, what we're doing with these is we're able to provide vertical wind profiles, which would be like a horizontal wind. So usually if you look at the weather data, it's at the surface from a weather station somewhere located in the mountains. And so we can go and look at a vertical wind profile. And what we've been able to show is that the winds are much stronger, especially in a downslope windstorm. A lot of these winds mix down a lot from aloft to the surface. And so during the Kincaid fire, we were allowed to they wanted us to go to a very non-interesting place, way up in a safe location about an hour from the fire, because they wanted to know where the winds when the winds hit that location. And we're like, oh, that's really great, that would be great, but we want to be in front of the fire. And so they request that. So that's kind of the useful information. We hope that we can potentially get some airborne aircraft on fires. So in terms of that, there's also Smoke management, so a lot of times if it's really smoked out because of temperature inversion, this happens in California a lot and all over the West, you can't operate the suppression aircraft. And so they want to know, like, so we launch weather balloons for the incident command. So they want those data and that information because they don't have the time to do that, and they don't have the expertise. So we've been called to a number of incidents where we couldn't deploy just because students were on vacation or it was too far or what have you. And so, yeah, so but a lot of these events, we get there before an incident command team shows up. And the reason being is we're interested in the ignition. We're interested in that extreme event. And in California, a lot of the big wind events occur, and then you have an ignition. However, that ignition occurred during a wind event. And we want to study the fire behavior during those events. So usually we're there doing our own thing. So during for example, during the campfire at 9 o'clock, we're driving around, and a battalion chief shows up, says, hey, what are you doing here? You need to go check in incident command. And usually they don't even care they know who we are in California, you know? And so we went to incident command, and it was just 2 people in front of a pickup truck. 3 days later, there were thousands of individuals, and it was a full camp with food and toilets and camping and, I mean, everything, and shelters. So yeah, long story short, we do help incident command teams, but we're usually tied in with the fire behavior analyst and the incident meteorologist. And we're hoping that through our presence that we can provide more of that data. We tweet it a lot, and it gets retweeted because a lot of people don't have time. Sometimes there's not a lot of internet connection out there. Anyways, thanks for the question. Yeah?
You mentioned for the small scale experiment, they all cut to the same height. So is it a lot different in different vegetation, different heights?
Yeah, and the problem with that is that the modelers would then have to go out and have, oh, I need to know what that shrub is. I need to know what that shrub is. And if you're talking about 1 kilometer by 500 meter plot, you want it as uniform as possible. So they cut that stubble because it worked, it matched the laboratory, but it's because that's what the landowner did anyways, because he was going to sell the material for grazing. I don't know what kind of plant that was, if it was wheat or something. But so it turned out like, oh, and they burn them all the time. So it was like perfect. That's what we try to do. It's like we're not going to go and set it up like, oh, you're going to burn your land? Oh, how many times? Can we show up? So yeah.
Would you say anything about safety tips if you're caught in a situation?
Yeah, this is. So the question was, would I talk about safety? I'm not a firefighter. I'm intimidated to be on the fire line because I have students with me, and even though I have a red card and I'm qualified, I'm nervous. Staying in the car doesn't always work, as you've seen in the paradise. There's an example from the fires in Portugal. People were in their home having dinner, and they heard about the fires, and they saw them in the hills. And they said, let's get out of here. So they drove, they got in smoke, they got in an accident, and they died. The whole family died in their car, and their house had no damage. And so it depends on the housing material and like what your landscape is. Don't be there. And one thing is, if there's an evacuation notice, follow it. And be prepared, like, because you're in fire danger land here. This is Intermountain West. You have fires, so have a kit, be ready, and if the time comes, you have to go and get out quick. So, yeah, I don't think I really answered it with much expertise there, but hopefully nobody has had to be in that impact. I've had students in my class that lost their homes to fires in California, and so. Any other questions? Yeah.
Can you explain why use radar versus LiDAR? What are the benefits of?
Yeah, great question. So the question was, why do we use radar versus LiDAR? The LiDAR is really nice for smaller smoke, but it attenuates on cloud, and it doesn't have the power to penetrate very far into the plume, so it doesn't have a long enough range. Whereas the radars have slightly more power. Well, they can have much more power. This is only 10 watts solid state, so we have like a 20 kilometer range if we're lucky. But it's dual polarized, which means that we can actually say something about the particles, where the Doppler LiDARs, they can't really tell us much about the particle size and the shape. They can just tell us how much backscatter we're getting off of that. So we want both. And actually we want 3 bands of radar and LiDAR, so we can look at different particle sizes and get a better idea of what we're sampling. So, yeah. And really, the truth is, I had a LiDAR, and we sampled 30 or 40 fires, and then we got a radar, and now we're going to sample a bunch of fires and then see what happens next. Yeah?
I was wondering if you've done any observations on when these columns collapse and come back down?
That is the goal. So the question was, have we made any observations of plume collapse, which is in the literature, or at least in the firefighting nomenclature. We haven't really, I've only seen a few cases of plume collapse. We haven't really observed a lot of strong downdrafts in the center of these cores. And that's what we're hoping to see. And it was surprising that the downdrafts are all on the edges, right? Because of the detrainment outside the column. And so we haven't, it's one of our research objectives to be able to sample that, but you just don't know what you're going to get because you don't know how the fire is really going to perform. But it's a great question. Yeah?
So when you visually look at the smoke, there's a spectral difference. You've got different browns, oranges, whites. Smoke. Sometimes when you look way down range, you can see on some fires it's still brownish, but on other fires it's becoming more gray. Can you comment on some of the colors going on in different parts?
You know, it's a question that some of it has different. Part of it is we don't really know. I don't really know. But one thing we do know is that if you look at the ash material on the ground, some of it's more black carbon and some of it's more mineral ash. And so you might be seeing more mineral ash, maybe more water vapor, maybe some more water droplets that you're seeing, water droplets in the smoke. But in terms of like shades of brown, I don't know if that's just, you know, I don't know what that is. Yeah?
On the one slide you showed there was some profiles from my modeling software. You said the profile didn't match in this one case very well. What things are being transferred from the research you're doing to that modeling software to do that?
Well, I'd love to turn it over to our modelers in the room, but I'll tell you. We're providing these data. They're downloadable links, and the modeling community can use these to run the models for the cases and test and see how they can improve the model. I use that as an illustration saying that, you know, we really do need observations here. Like, this is really what the observations are showing, and you know, the average of the model and the average of the obs aren't matching up, and that's okay. So then you can argue, well, where's the model grid point? Where's your observation? Of course, it's not going to match, but I'm an observationalist, so I thought that was a nice biased data to show. Yeah, so I believe the modelers are actually using these data to help tune their prediction systems, and it gives them kind of some bounds to think about. Because I see this all the time, and I think we all do in this community, is see, oh yeah, I simulated this fire. And it's like, really? Because that's not really how it happened. I know your model showed that, but that's actually not what happened. And the input data are not, you know, very good. So anyway, so that's kind of why. It'd be better input data to simulate it.
Let's take one more question here.
Okay.
So when you were talking about the big vertical velocity particles or parcels inside of the plumes, have you looked at any correlation with that with the atmospheric stability?
People have, actually. People have looked at stability on plumes. There's people in this audience. And so in this case, we haven't yet. We have. Actually, what happens is, what's interesting about that Pioneer fire with the aircraft is that it was below cloud base. So we expect when you get latent heating with the cloud form that you would have even more acceleration. And what the model suggests is that you get a maximum near the fire. So it should be really, the fire's really hot. Fire's like 1500 degrees C, okay? So you've got 1500 degrees C parcel punching vertically through the atmosphere. But then there's a secondary velocity increase aloft, and that's potentially due to latent heating in the cloud, and so you might get that second velocity increase. We didn't see that in our data, and we thought, oh, this is interesting, that the model may not, and it's actually below the plume height, or the cloud base. So we don't have the answer for that, but there are some ideas. So plumes punch up through the stable layer, and then they can actually come back down, and they will detrain on top of the stable layer and not come back down on the ground. We've seen that. I showed the slide, I just didn't talk about it. So, but that is a big question, and there's still people looking. I was at a conference the other day where people are looking at stability and plume dynamics. So, yeah, when using a model, this is where the data and using data in a model allow us to investigate that better. You know, we're out here, we have maybe one radius-on sounding, if we can launch it, so we can get some ideas. Yeah.
All right, before we thank Craig again, I want to thank all of you for being here, especially all the students and in-STEM students. I have a question for you from the organizers. How was the dinner beforehand? Was that a good incentive to be here? Yeah, okay. I think that'll become a tradition now.
It was a good turnout.
So let's all thank Craig again.
Thank you. Good, thanks. Timing was okay?
Oh, that was perfect.